Welcome to the webinar, Going Green, Alarm Management for Greenfield Projects. My name is Todd Stauffer. I'm the Director of Alarm Services here at Exida. And what we're going to talk about during this webinar is a bit of a hodgepodge of different topics with a goal of focusing on applying alarm management principles to greenfield or new projects or sites. So we'll look at why alarm management is important. We'll talk a little bit about the status of the current alarm management standards, talk about some key principles of alarm management, including the rationalization process, and then we'll talk about how to apply that to greenfield projects with a particular focus on and tie to alarms that are part of your safety system design or your risk reduction methodology. So first, a little bit about who Exida is. We're a global supplier of products and services for cybersecurity, alarm management, and process safety. We're an industry leader in the certification of people and devices when it comes to process safety and security. If you've worked with a safety instrumented system and have designed one with SIL compatible or SIL capable instrumentation, chances are that what you've been working with is instruments that have been certified by Exida. We also have a large suite of software tools for design and engineering of safety instrumented systems, tools for PHA, SIL verification, SIL selection, and included in that list we call a tool called SIL Alarm, which is a tool for alarm rationalization, which we will talk about during this webinar. We consider it a part of our safety system tool suite because we consider alarm management to be an important part of process safety. We're also a strategic partner for Emerson in the area of alarm management. So speaking of alarm management, let's talk about the state of alarm management in a typical process plant. What does the operator see in the control room? Now, what we find is that most operators in your typical control room are inundated with considerably more alarms than they can reasonably deal with on a steady state and continuous basis, in some cases an order of magnitude more than what the standards and guidelines recommend. They also receive more alarms than they can handle during upset situations, and they are flooded by alarms, making it very difficult for them to respond correctly and appropriately. We also subject them to nuisance alarms. In a lot of cases, they have pages and pages of standing or stale alarms. These are the alarms that are always present on the HMI console, making it difficult to see new alarms come in. And we'll talk about alarm priority and how important that is for the operator. And the key to prioritizing alarms and making sure that you can differentiate what your most critical alarms are. By not prioritizing alarms appropriately, it's difficult for the operator to know which alarms to respond to first. And of course, with all of these problems in play, it can lead to operators missing critical alarms, which can result in unplanned downtime, damage to equipment, people being hurt, off-spec product, and in worst cases, accidents. And we really do believe that alarm management and process safety go hand in hand. One of the purposes of the alarm system is to help keep the plant safe and personnel safe, in addition to help you optimize the process. So alarms are typically one of the first layers of protection, the alarm and the operator response to the alarm. One of the first layers of protection used in conjunction with a safety instrumented system and with other IPLs, passive IPLs. And one of the things that has been found is an investigation of some of the worst case process safety accidents, things that have been in the news for a long time recently and in the far past. One of the common denominators or common themes of the accidents that you see listed here was that poor alarm management was a significant contributor in each of these process safety accidents. So we really do think that alarm management and process safety work together, and that becomes particularly true when we talk about alarms that are part of the safety design. That is, alarms that are identified as safeguards in a HAZOP or a PHA, and alarms that are identified as independent protection layers in a layer protection analysis. So let's take a look at one of those accidents that was listed and see how alarm management played a part in it. So Deepwater Horizon is something that probably everyone, or I would hope that everyone, is familiar with. Probably most familiar with the element related to the spilling of oil from the Macondo well blowout in the Gulf of Mexico. What's probably not quite as well known is what happened to the platform itself, the destruction of the Horizon platform, and the causes of what went behind the design there and why 11 people lost their lives and multiple other people were injured. So let's take a look at the design of the alarm system on the Horizon. So there were numerous tens of sensors placed all around the platform with the goal that, or with the design intent that, if any one of them detected the presence of gas or fire, it would alarm in the places where people were, 3 different places: the bridge, the drill shack, and the engine control room. And it would also automatically sound a really loud horn to tell everyone that they needed to evacuate the rig. That was the design, the intent of the alarm system design there. But the way it was actually implemented was different. They were concerned about false alarms or nuisance alarms in the middle of the night, waking people up and telling them to evacuate when they didn't really need to evacuate. So with that concern about these nuisance alarms, they decided to disable or inhibit some of the alarm enunciation, putting the decision about whether to hit the evacuation horn into the hands of the bridge operator, with the idea that if the sensors detected gas or fire, the alarm would only go off to the bridge operator, and it was up to them to decide whether the evacuation horn should be pressed. So now you can see, you can read for yourself information that comes from the testimony before U.S. Congress. This was the actual operator that was on the console at the time. And you can see that she was somewhat overwhelmed by all of the alarms coming in at once, not knowing what to do. She wasn't there by herself, though. She was also joined by her supervisor, who also was having difficulty understanding what to do. The alarm enunciation was making it difficult. The overload of the alarms was making it difficult for them to think and determine a course of action. And of course, remember I said it was up to them, the bridge operators, to make the decision about whether to sound the evacuation horn. And unfortunately, there was a delay of about 10 minutes between when the sensors first detected the gas and fire to when that evacuation horn went off. I have to believe that that contributed to the number of people that lost their lives or were injured in that accident. So directly the effect of poor alarm management. So how did we get into this situation with too many alarms, alarm overload, people not knowing how to respond when they get hit with so many alarms? If we think back to the olden days in panel board control rooms, there was actually limited real estate, limited room for alarms. So maybe for a given unit, you might get 200 alarms. That was all there was space for. So the engineers designing the alarm system had to pick the best 200 alarms. They had to do their due diligence because they only got 200 alarms. So they really had to optimize and trade off and think about what the purpose of each alarm was and what the operator was going to do. Besides having a limited real estate to work with, there was also a significant cost because these were hardwired alarms. They had to be wired up. If you compare that situation to today's modern DCS, where alarms are in software, alarms are essentially free, and people treat them as such, with the idea that if you're not sure whether you need an alarm, then you might as well enable it. And that's part of the thinking that has gotten us into the problem that we have now with too many alarms. So one of the things that we want to do is to get back to the thought process that we used to use, where we thought about whether the alarm was really needed, what its purpose was, what the operator was to do, and that's a process called alarm rationalization, which we'll talk about some during this webinar. So this process of alarm rationalization, in today's world or in the past, when did it usually get executed in the lifespan of a project or a system? Well, if we think about time going from left to right, and in the origination of a project, starting with maybe a HAZOP and going to a LOPA if it was needed, and then the design of the P&IDs in conjunction with that, and then the configuration of the control system leading to the startup of the control system. The actual rationalization activity may not occur for months or years after the system has started up and been running. So you're essentially starting up a system without a well-designed or well-thought-out alarm system. So no wonder operators get inundated with alarms. If the system hasn't received any rationalization before starting up, that's exactly what would happen. So one of the questions that I wanted to ask as a poll is, how often have you found that an alarm which was identified as an IPL was not valid or is ineffective? The idea being that in that time flow that we looked at, since alarms are identified as safeguards and IPLs early in the project and not rationalized till after the system has been running for a while, it's very possible that when you finally get around to rationalization, you might find that some of the alarms that you identified as safeguards or IPLs are not valid, don't work, don't provide the risk reduction. So the question then is, how often in your experience have you seen that happen? And we're getting a few responses. Give another couple of seconds. As soon as the results have flattened out, and I'll make it so that you can see them now. You can see there was over 50% of the respondents said that sometimes or frequently they find an alarm that's an IPL turns out to be not valid or ineffective. And part of the reason why that occurs is because of that huge time discontinuity that we just saw. So one of the things that we want to talk about for rationalization of greenfields is how to prevent that. The poll that we just did is also similar to a more detailed study that was done about a year ago that looked at alarms and safeguards, alarms as safeguards and IPLs, and how they're treated and designed. And in this case, there was over 200 safety practitioners that were polled that same exact question, and a good 65% of the respondents said that sometimes or frequently alarms that were IPLs turned out to be not effective. And what does that mean? What that means is if you're counting on your alarms to be part of your risk reduction strategy, then the fact that they're not working or they're not pulling their weight in terms of risk reduction means that you'll need to either make up that loss of risk reduction by increasing or adding other IPLs or increasing the effectiveness, like your safety instrument system, changing it from a SIL 1 maybe to a SIL 2, which of course has cost impact, it has maintenance and testing impact. So that's if you realize and know that that's happening. If you don't realize that your alarms aren't doing what they're supposed to from a risk reduction point of view, you may actually be operating with an actual risk that's greater than your tolerable risk, which would not be a good thing. So that's part of what we want to discuss and address. So if the typical time to rationalize alarms is after, months or years after the system has been up and running, and the operators are complaining about the alarm system performance, if that doesn't work, how should we do it differently? What could be different? Well, the end users of today have gotten smart to that situation and said, we no longer think it's acceptable to start up a system without the alarm system being rationalized, without the alarm system being configured appropriately. So that means rationalization has to take part before startup, likely in parallel or in iteration or iteratively with your HAZOPs, your LOPAs, and your DCS configuration. So that's part of what we want to talk about. To get the information, or where should the information come from regarding what we do for alarm management practice and principles? There's two main sources of information for that. There's the EEMUA 191 guideline that was created originally in 1999 in response to an accident in the UK. It just came out in its third edition in 2013, September 2013. And then there's also the ISA 18.2 standard created in the US in June of 2009. This is actually a true auditable standard with requirements and recommendations that you clearly need to look at and address how you're going to comply with, because OSHA deems this document as recommended and generally accepted good engineering practice. So it's RAGAGAP. That means they expect you to follow this as good engineering practice. If not, if they were to audit you and you're not following the standard, then you could be in line for some fines or some action. Now, this document was also given to the IEC, the International Standards Creation Board, to become an international standard, and it's on track for that to happen sometime later this year or next year, with the idea that the international version of the alarm management standard will be largely based off of the original ISA 18.2 standard. One of the things that standard defines is an alarm management life cycle or workflow process. If you're familiar with the functional safety life cycle from the 61511 standard, this will be familiar to you. Different stages that talk about the activities and requirements of what you need to do. In the case of alarms that are safeguards or IPLs, they actually are part of both life cycles. They're part of the safety life cycle in hazard and risk assessment and allocation of safety functions, and as part of the alarm management life cycle. And you can see the connectivity there. But the alarm management life cycle primarily lays out a workflow. So now I wanted to get your assessment on where your company is in the adoption or use of alarm management standards like ISA 18.2. So is it something that you haven't done much with, you're aware of, but have taken no action yet? Some actions have been taken, but maybe not coordinated in a comprehensive plan, or you do have a comprehensive program in place, or perhaps this is not applicable to you. So take a second and think about what your answer would be to that question, and then I'll share that with the group. Okay, hopefully you can see the results now. The most popular answer was that some actions have been taken, so that's a good sign. We have a few people that said they were not aware of the standard or of not taken any action, so maybe that's a follow-up item from this webinar to start to get more familiar with that. I noticed that nobody said they have a comprehensive program in place. And that's understandable that when standards like this come out, they're not put in place and users and vendors don't achieve full compliance with it overnight. It certainly takes a period of time. So the adoption process is a gradual curve, and hopefully what we're seeing here is the start of increased adoption. So now let's talk about some of the other important items related to alarm management that come out of those standards. The ISA standard itself defines what an alarm is supposed to be. An audible and or visible means of indicating to the operator, with the emphasis on operator because they're the target audience for the alarm system. If the alarms that are displayed through the alarm system are not understandable and actionable by the operator, then they really don't belong in the alarm system. Also, an alarm needs to indicate an equipment malfunction, process deviation, or abnormal condition. Essentially, that something is wrong, something unexpected has occurred. And then last but not least, that it requires a response from the operator, more than just acknowledging the alarm or silencing the horn, something that is designed to address the abnormal situation, turning on a backup pump or opening a valve, something like that. Other key design principles, as part of rationalization, we actually want to define what the operator is supposed to do. And we'll use that as a criteria for determining whether it's a valid alarm or not. We also want to make sure there's enough time for the operator to respond, not too much, not too little, and that any time an alarm is presented to the operator, that it's useful and relevant. So, for example, when equipment is out of service, many times the alarms coming from that piece of equipment are no longer valid to the operator, so the ability to be able to suppress them or not present them when they're actionable is very important. We also want to make sure that when an upset occurs, the operator doesn't get 10 alarms that all basically indicate the same thing. We strive for uniqueness. One upset, one alarm. You only need one alarm to know that something has happened and what you need, and to indicate what you need to do. So one of the problems and causes of why alarm systems are overloaded is, in a lot of cases, it contains other stuff besides true alarms. And if you look at this little matrix, it's a good way to identify what a true alarm is. It should be an abnormal condition and one where the operator must take action. Probably if you have an unrationalized system, you have a lot of these other types of notifications in there. Maybe it's an abnormal condition, but the operator doesn't need to respond, or maybe it is an expected condition. Well, all those kind of things, while they might be valid and useful for the operator to see, don't belong in the alarm system. They really should be segregated out and presented to the operator in a different way. Now, we talked about an operator response. Well, what makes this response successful? If we think about what they need to do, first they need to detect the presence of the alarm. If the HMI has lots of flashy colors and graphics and a bunch of nuisance alarms already blinking, it may be very difficult for them to detect the presence of a new alarm. They also need to diagnose or figure out what the problem is and then perform the appropriate corrective action, which could be going out into the field, calling a different operator to go do something, to walk out into the field and grab a wrench and walk to a certain piece of equipment and do something locally. So this could take some significant amount of time, on the order of minutes. We'll look at that as the operator response time. Now, if you put yourself in the shoes of the operator, if you were a new operator, and you were working shift and an alarm occurred, what would you want to know? What information could help you do your job better? Well, if there was a way to present an alarm response procedure, what has caused the alarm? What do you need to do in response to it? What's going to happen if you don't respond? How much time do you have to respond? And how do you confirm that the alarm is real? presenting that kind of information in context when the alarm occurs would certainly help the operator's performance in terms of timeliness and consistency. So the next poll question then is, does your company make these alarm response procedures available to the operator? And if so, in what format? So hopefully you all can see the survey results quite across the board. 25% say no, you don't make alarm response procedures available to the operator, and then there's a variety in the different formats, with 16% saying that they're integrated into the actual HMI, which is probably the best scenario, or the best that you can do. Now, the reason I ask about these response procedures is because it's actually a requirement in the ISA standard that they shall be readily accessible to the operator. Now, that doesn't dictate what method you use. Could be paper, could be electronic, but the fact that you're thinking about it and making sure that that information is going to be available for the operator, or that you're doing things up front in your project to make sure it's easy to create these procedures later on, is a good idea. You can also see the impact that having an alarm response procedure has on the safety element of using an alarm. So if you're counting on it to provide risk reduction, then certainly the presentation of an alarm response procedure can help increase the reliability of the operator's response. Here's the results when that more detailed survey was conducted a year ago. About 3/4 of the people said that they do provide alarm response procedures. Of that fraction, the majority were paper manuals. So, which is certainly achieves compliance with the standard, but in terms of making it as effective as possible for the operator, we can probably do better if we can take the information and make it appear in context electronically, either within the HMI or some other way, making it so the operator can quickly know what to do. So now let's briefly go through the rationalization process, and then we'll see how it all applies to a greenfield project. So rationalization is when we review the existing or potential alarms, make sure that they meet the criteria for being an alarm, and including documenting their cause and their consequence, corrective action, assigning priorities and limits and things like that, recording the information in a master alarm database. So one of the first things that you can do to determine whether the alarm is valid or not is a series of, I'll call them go, no-go questions. Number one, does the alarm indicate a malfunction, deviation, or abnormal condition? 2, does it require a timely operator action in order to avoid defined consequences? Is it unique? Is it the best indicator? Ideally, you want to answer yes to all 4 of those for each alarm that you're looking at, or else it's not a valid alarm. And part of the reason why we go through this is to think about whether you can't ask these questions or think about these topics any time you identify an alarm, such as during a HAZOP or when you're considering an alarm during a layer protection analysis. If this is the criteria, part of the criteria that you use to determine that it's a valid alarm during rationalization, sometimes it might make sense, or in a lot of cases it might make sense, to ask these questions earlier in the process, earlier in the design, at the point that someone nominates the potential alarm. As part of rationalization, then, we also document the objective of the alarm. What is the likely cause? We want to make sure it's an unexpected situation. We document what the likely consequences are if the operator doesn't respond to it. We want to also document what's the operator to do, what's the corrective action. If we can't define corrective action, then the point really shouldn't be an alarm. And ideally, we also want to document how they can confirm that the alarm is valid, either looking at other process measurements or maybe a local site gauge or something like that to help them to verify that if the corrective action is to press the emergency shutdown button, that they in fact do need to do that, and to help corroborate that that's the action they need to take. So we would document those 4 things, and based on the analysis, that helps us know whether the alarm is even valid or not. Document those results in the master alarm database. In this case, showing an example, if you use the exida SIL alarm rationalization tool as your master alarm database and document the cause, consequence, corrective action, that was the same stuff that we talked about earlier would be ideal to present to the operator in an alarm response procedure. So what we advocate doing is, if you go through this rationalization process and document this element of the alarm design, when you're all done, you can take that information and turn it into an alarm response procedure with minimal additional work. In this case, we're showing an example of a integrated alarm response in a Delta V system, a faceplate called Alarm Help, which can be accessed from the tags faceplate or the alarm summary list, where the information that's displayed can actually come from rationalization, helping the operator to know how to respond to that alarm. Another key part of rationalization then is defining the alarm's priority. And priority is what the operator uses to know, what alarm do I respond to first when there's multiple alarms. And if you work in a plant that never has more than 1 alarm active at a time, good for you. You probably don't need to be listening to this webinar then. But for most of us, that's not the case. So we need to define a way for the operator to know which alarm is most critical, or how to evaluate what's more critical than another. And the way that's recommended is to evaluate the severity of the consequences in different predefined areas, and to assess the amount of time that's available for the operator to respond. Typically assessed in a matrix similar to this. We can define the different consequence areas, such as personnel, environmental, financial, and then we assess how much time the operator has to respond, take the worst case consequence and combine that with the amount of time that the operator has to respond, and that gives us what the priority of the alarm should be. Now, one of the things that makes sense, if possible, is if you look at this consequence matrix, it looks an awful lot like the same structure of a risk matrix and a PHA. If possible, if you have a risk matrix, it's great if you can reuse all or some of that as part of the creation of this alarm prioritization matrix, as a means of driving consistency in your evaluation. In some cases, the risk matrix is too exaggerated to work for alarms, but it's definitely something to take a look at as a means to keep consistent in your risk evaluations. So within the SIL alarm tool, we can automatically calculate the alarm priority based on our assignment of those consequences, assessment of those consequences, and time to respond. Or we could say that the alarm really isn't an alarm. It's one of those other types of operator notifications, like an alert or a prompt or something like that. So we could indicate that the point is not really an alarm, might be valid information for the operator, but doesn't belong in the alarm system. We can also classify the alarm, assign it to classifications, and what's really important then, and early in a project, early in the design process, is to indicate whether the alarm comes from a HAZOP report or analysis, or multiple HAZOPs, or a layer protection analysis, indicate where it comes from. So we can actually create a cross-reference of where that alarm is referenced or used in the safety design, so that if we need to go back to affect or see how the impact of an alarm design change affects the safety design of the plant, we can easily do that. We also, during rationalization, review and assess the alarm limit, looking at the process dynamics and the consequences that we're trying to prevent. We can also enter information for the deadband. We can set the deadband appropriately or on-off delays to help us reduce the chattering of the alarm and minimize the chance that it turns into a chattering alarm. If the system supports manual suppression or shelving by the operator, we can configure that information. And we can also then define if there's any scenarios where the alarm needs to be suppressed or have a different limit or priority. In this case, we're showing suppression of alarms following a compressor trip. First, we define the conditions that we would look for to know for sure that the compressor is tripped. Then we would create the list of alarms that we think could be or should be suppressed in that scenario. We can define a common alarm to present instead of the multitude of alarms. We can also check to make sure that it's okay to suppress the alarms by looking at what their priority is or their classification, or whether they're a safeguard or or an IPL. Certainly, if they're a safeguard or an IPL, you want to think harder about whether it's acceptable to suppress the alarm and make sure that the hazard that alarm is there to prevent doesn't still exist in this state or in this scenario, because if it does, then it wouldn't be acceptable to suppress the alarm. Or you may find that there's a different hazard and the alarm still needs to be there to prevent this new different hazard that makes itself apparent during this unique state of the plant. So if we now look at how we would do rationalization in this new methodology of ensuring that rationalization occurs before startup of the plant, and we don't want to delay the startup for months and months and months. That means rationalization needs to go on in parallel with the HAZOP and the LOPA and the configuration of the DCS in parallel, and it would also probably be iterative between those to some degree. So let's look at how that works, or the key things there. So we're going to start with design information that we'll use and we'll bring into the master alarm database to use for rationalization. And the input could come from multiple sources. It could be from your P&IDs, it could be from your HAZOPs. We'll get some relevant information from there. If you have a safe operating limit table, for example, that would be relevant information to bring into this master alarm database. But we want to aggregate and collect all that information so that it's available, readily available when we conduct rationalization, with the idea that then when we're done rationalization, we have an output of information that can be used to configure the DCS, to specify how it needs to work, an Excel spreadsheet of the settings, or the creation of the alarm response procedures. So that's kind of the methodology of how this would work for a Greenfield scenario. And when we're doing the rationalization, we are, instead of looking at all the existing alarm conditions that maybe are already in the DCS, we're instead focusing on what are the undesirable situations that we want to prevent in this unit or with this piece of equipment. And that'll dictate what alarms we need. What alarms we need to be able to sense that, and what alarms we need to prevent that undesirable situation or consequence from occurring. So we're not going to be going, oh, we need a high flow and we need a low flow because we're measuring flow, so we need alarms there. No, the idea is to step back and kind of apply a HAZOP type mentality and think about what is it you're really trying to prevent, and what alarms do we need to make that happen. So for example, here's a HAZOP that calls for the need of a couple of alarms. Now, hopefully one of the takeaways, if you're involved in PHAs and HAZOPs and LOPAs, is that now that you understand a bit more about the alarm rationalization process, and what it takes for something to be a valid alarm, that you can actually apply some of that thinking at the moment in time when you specify the need for the alarm. This would certainly then help to make sure that later on down the line you don't find out that the alarm that you added to your HAZOP or your LOPA is not valid and you need to redesign your risk reduction. So one way to actually make that happen and to capture that information that I just talked about is with the tools that you're working with to document your PHAs. In the exida PHAX tool, there's the ability is provided to document some of the alarm rationalization information. So anytime you indicate that you have an alarm as a safeguard, you can also then document what the operator's corrective action would be, how much time you think they have to respond, what the actual consequence would be if the operator directly didn't respond. So a lot of information that you would need for rationalization, and you have the right people in the room probably to talk about it, so it makes sense to document some of that information. I'm not suggesting that you do a rationalization at the same time. That's a bit more work than what's necessary or called for, and would certainly take your PHA off track. But I think some nominal documentation of what the alarm's purpose is would be very beneficial. Now, when it comes to documenting or defining the consequence, to some degree, this can be very tricky for people that do both PHAs and alarm rationalization. In a PHA, you're concerned with or trying to identify the ultimate consequence. What could happen if every layer of protection fails? In alarm management, we want to find out or identify what happens directly and immediately if the operator doesn't respond. So in this scenario here, the consequence for alarm rationalization, if the operator does not respond to the alarm, is the trip of the safety instrumented system. The consequence in the PHA would be this explosion or fire or whatever it is. So that means that in this case, the way the layers of protection are designed, the operator's response to the alarm is not the last layer of protection, which is good. That's what we'd want. So we need to factor that in identifying what the consequence is, because we're going to use that mitigated consequence when we calculate what the priority should be. We also want to assign how much time the operator has to respond and think about how that's applied during your HAZOP and your LOPA, with the idea that when we talk about operator response time, what we really mean is how much time is available for the operator to respond. So that's the time from the activation of the alarm until the last moment that the operator action will prevent the consequence. So we want to make sure, since time can show up in HAZOP, in LOPA, and rationalization, that we're using the same definition of what time is. Now, certainly if there's insufficient time available compared to the time needed, then that means the alarm would not be valid or is not going to work. And you can't take it as a layer of protection, and you shouldn't take it as a safeguard, and you need to actually automate the response somehow, maybe by an interlock. So one of the things that is typically done is if you're going to take alarms as an independent protection layer, you define the criteria for how much time the operator must have at a minimum to respond to the alarm to be able to take that as a layer of protection. And the reason you do that is if you're assuming a risk reduction of 10, a probability of failure on demand of 0.1, that means that you're counting on at least a 90% reliability or 90% probability that the operator is going to respond successfully, even during this upset scenario when probably this alarm would occur. And one of the ways that you can help to make sure that he can deliver that level of reliability is to make sure that they have enough time to respond to the alarm. Oh, in addition, make sure that you have alarm response procedures for them as well. But judicious defining of what the operator response time is for your IPL criteria can also be incorporated into when you're doing your alarm prioritization. If you set your priority time buckets with the knowledge of what the criteria is for an independent protection layer, we can say that, for example, here, since 15 minutes to 30 minutes is one of the thresholds, that if we're going through rationalization, one of the outcomes of doing this is we will know that any alarm that had a time to respond of less than 5 or 5 to 15 would not be a candidate to be an IPL unless there was some redesign done. So smart connection of the priority matrix to an understanding of what the time criteria is for IPL definition will make it so one of the outputs of rationalization is those alarms that are candidates to become an IPL. Now, as mentioned earlier, it's also a best practice to record for sure if the alarm is identified in a HAZOP or an LOPA, where it comes from, so that there's coordination, traceability to changes from both sides. Now, when you set the alarm limit, you're typically trying to set it based on what you know about the normal operating envelope, which you may not know in a Greenfield scenario. So it can be a little bit trickier to set the alarm limit. But if you set the alarm limit in relation, or you think about what it is you're trying to prevent, that is the consequence, and you set the alarm limit in relation to that, you may still be able to establish a valid set of alarm limits even early on in your process when you look at what your pressure relief valve settings are. So if this was a pressure measurement that we were looking at, and we knew that the next layer of protection to kick in after the alarm was a relief valve, if we knew what the pressure setting was for that, we could use that as the reference point in setting the alarm limit. So if we know our design limits, our safe operating limits, our maximum design pressures and temperatures, that can go a long way to help us define what the alarm limit should be. So understanding and documenting the alarm limit and its relation to those operating constraints, that process safety information, is definitely a good idea to do, because then you can also see how, if that information changes over time, which it always does to some degree, that you can see the need to adjust your alarm limits. So looking at an ideal Greenfield scenario, then, we can execute the alarm rationalization in parallel using the input from the plant design process, the P&IDs, the HAZOP work, safe operating limits, that information, process narratives. We can use that to drive the creation of the master alarm database and the rationalization done in parallel with the configuration of the DCS, so that when you get to a certain point in the project, you can match those two databases together and bring all the alarm settings from the rationalization tool into the DCS configuration and update the alarm settings. So allowing those two tasks then to be done effectively in parallel. And of course, as part of this, early in the design of a project, the inputs that go into establishing what the limit should be and what's the cause and consequence, a lot of that is going to change along the way. So you have to be able to identify those changes and track those changes particularly as they impact the alarm design. So one of the things to look for in a tool is the ability to track those changes, not just from the DCS configuration, which in this case is actually an output of rationalization, but the inputs that go into it, your P&ID program or your safe operating limits in a spreadsheet. And we're happy to say that the SIL alarm tool allows you to capture changes from any of those databases. So summarizing or coming to some of the conclusions, when you're defining alarms, you want to make sure that you're thoroughly documenting the tag name. One of the things that you often see is that the alarm and tag names that are used up front in the P&IDs or the HAZOPs are not very precise, or are not the actual tag number that ends up in the DCS configuration in the control system, which is what the rationalization database is probably going to need to use. So understanding that and making sure that you're thoroughly documenting what you know will help somebody else to be able to use that information. So we definitely want to pay attention to our tag naming conventions, because certainly if you're doing a PHA or a HAZOP and you're identifying an alarm, you need to count on the fact that the alarm management team is going to need that information and need to integrate that information into their work. So the more you can do to accurately assign what tag or what alarm that belongs to, the better. Because if you just say it's the tank high level alarm, that's going to create a lot of extra work when the alarm management team has to go off and figure out what ID tag that actually is. Definitely would recommend that for safety practitioners, when you're executing HAZOP and LOPAs, that you incorporate some of these alarm management principles that we just talked about. What makes for a good alarm, the definition of an alarm, defining what the consequence is and the operator corrective action, with the idea that that will help make sure that any time you propose an alarm, that it's likely to come out to be acceptable when it goes through the rationalization process. So making the preliminary assessment of the alarm's validity at the point that it's defined, rather than months or years later. And also then knowing that somebody's going to have to come behind you and use that information, make it easy for alarm information to be extracted. Different tools have different ways to do that, to set up flags to uniquely identify alarms. But again, thinking that somebody else is going to have to use that information and put that into their work process, make sure you make it easy for them. And certainly, hopefully, we've seen that if you follow these best practices and these conventions and the information is available, that it is possible to execute an effective alarm rationalization up front in the design of the plant and the process. You don't have to wait until after the system is up and running. You can do it in the feed phase or other early design process. And then the final takeaway is really that for the process safety and alarm management teams, hopefully you see that really need to work together when it comes to effective design of alarms that are used for safety purposes, and getting to know a little bit more about how the other party uses the information and how it goes back and forth can help each of us do a better job of defining it in a way that it's easier for that other party to use. So certainly think about that. And with that in mind, one of the things that we've added, one of the things that's been added to the CFSE program is something called an endorsement program, which is a series of specialties that you can look to learn more about and to demonstrate that you're an expert in it, to show that you have competence there. So for alarm management, if that was something that if you were a CFSE or a CFSP and interested in learning more about the topic and being able to demonstrate that you have some level of mastery for that, we have this endorsement program for alarm management, which has a training class associated with it, a study guide, sample questions, and it's got an online exam, 40 questions to help you validate that you understand the concepts of alarm management. If you want any additional information on that, go to either the exida website or the CFSE website would probably be the best one to go for that. So with that, we've reached the conclusion. We're just about out of time, but let me see whether there's any questions. So one of the questions is, if during a HAZOP, if credit is taken for an alarm as a safeguard, does this alarm now need to be considered an IPL? Depending upon the point of view of that question, if it is a safeguard, it is a candidate to become an IPL, but it may not meet the requirements of being an IPL, and you may not even need to do a LOPA on that particular cause-consequence scenario. But certainly safeguards, alarms that are safeguards, is a much larger set of values than alarms that are actually independent protection layers. So every IPL is a safeguard, but not every safeguard makes it to be an IPL because it doesn't meet the strict, rigorous criteria of being independent and auditable and things like that. So if the alarm is identified as a safeguard, it then is a potential candidate for being an IPL if it was needed and if it met that criteria. So the next question is, what happens with a plant in operation? Is it possible to also do a rationalization of the alarms? And it certainly is. That's more along the lines of what's typically done, where after the system is up and running for months or years with the alarm system performance that we saw early on, that a rationalization is conducted, and that helps to improve the performance. But it's actually much easier to eliminate alarms when you start from a clean sheet of paper than it is after they've been in the system and have been running. So, because even though they might not meet the criteria for an alarm, there's always that hesitancy to get rid of it if you know that people might still be relying on it to operate the plant. So, very good question. On that note, we will wrap up and I will say goodbye and thank you for attending. I hope that you found this webinar to be useful. As a follow-up from this, you'll get an email with a link to the recorded version of the webinar as well as the presentation. And I encourage you to take a look at the exida website for more information about alarm management and the CFSE endorsement program if that's of interest. And also my email is shown here at the bottom of the screen. If there's any questions that come to mind after this, please feel free to shoot me an email with your comments or your questions. Thank you, and have a good rest of the day.